Hi everyone! Today we are going to discuss subgradients. This will be used in the next lecture to create a subgradient-based optimization method. First, we will define subgradients. We already did that a few lectures ago, but we will quickly do it again to refresh our memories. Then we will look at some concrete examples. Similarly to how we have calculus rules for the normal gradient, we will discuss some of the calculus rules for the subgradients. Our motivation comes from gradient descent that we discussed during the last lecture. With gradient descent, we were able to create an optimization method for differentiable functions and analyzed its convergence rate. We proved that when the gradient is Lipschitz continuous, then gradient descent can achieve big O 1 over k convergence rate. We would like to investigate if we could create a similar algorithm for non-differentiable functions as well. Many important real-world optimization problems are convex and non-differentiable. It would be great if we could have a simple optimization method for this class of functions as well. Since the gradient descent method was very simple, we would like to have a similar optimization method for this class of functions. As a reminder, the gradient descent update rule was just this: xk equals xk minus 1 minus step size tk times the gradient of f at xk minus 1. Here, k is the iteration number, tk is our step size, and we start this update rule from some x0 n-dimensional point. We will be interested in optimizing convex non-differentiable functions. As a reminder, when a function f is convex and differentiable, then we have this important inequality which states that the first-order Taylor series approximation of f is a global underestimate of the function. Formally, f of y is at least as big as f of x plus the gradient of f at x transposed y minus x for all x and y. Some lectures ago, based on this inequality, we defined subgradients for convex and possibly non-differentiable functions. We say that at location x, the n-dimensional vector gx is a subgradient of function f if the f of x plus gx transposed y minus x linear function in y is a global underestimator of the function f. Any gx that has this property is called the subgradient of function f at location x. Note that technically we could use the same definition of subgradient for non-convex functions too. In practice, however, calculating the subgradient for non-convex functions can be very difficult, and we will be mostly interested in the case when function f is convex. When function f is convex, then we can prove that at any point x, the function has at least one subgradient. However, when the function f is non-convex, then the subgradient might not exist. The gradient is a local property of function f at x, meaning that we can calculate the gradient of a differentiable function, even if it's non-convex, just from the function values in a small neighborhood of x. However, the subgradient gx is a global property of function f, meaning that we require this inequality for all y in the domain of f. And when f is not convex, then it's not enough to consider the function values only in a small neighborhood of x. As we discussed before, at any point x, there could be many subgradients of function f. The set of our subgradients at point x is called the subdifferential of f at x, and it's denoted with this partial derivative sign delta f of x. So the subdifferential set of f at x is the set of all g n-dimensional vectors such that g is a subgradient of function f at x. Let's discuss some of the important properties of the subgradient and subdifferential. The first lemma I would like to mention is about the existence of the subgradient. We can prove that if we choose any point x in the relative interior of the domain of f and f is convex, then at least one subgradient gx exists at that location x, even if f is non-differentiable at x. We are not going to prove this now, but I leave here a link to the proof of this theorem. The proof uses the supporting hyperplane theorem of convex functions and the fact that the epigraph of convex functions is a convex set. The next important lemma I want to mention is about the uniqueness of the subgradient. This lemma claims that if function f is differentiable at x, then the subgradient is unique. In other words, the subdifferential set contains only one vector, and that vector is the same as the gradient at that location x. We are not going to prove this either, but I'm listing here some pointers where you can find the proofs of these lemmas. Please note that the reverse of this lemma is also true. When the subgradient is unique, then the function is differentiable and the subgradient is the same as the gradient. Here are some other important properties of this subdifferential set. The subdifferential set at the location x is always closed and convex, even for non-convex functions. As we discussed earlier, if function f is convex, then the subdifferential set is always non-empty. However, if function f is non-convex, then this might be an empty set. The next two properties are about the uniqueness of the subdifferential. If function f is differentiable at x, then the subdifferential set contains only one element, and that is the gradient. And finally, if the subdifferential set has only one element g, then the function f is differentiable at x, and the gradient of f at x is this vector g. Let's see some concrete examples. The first example we are going to look at is the absolute value function. We know that when x is not 0, then this function f is differentiable, and therefore the subgradient at those points is just the derivative of function f. This derivative is the sine of x, that is, when x is less than 0, then this derivative, and thus the subgradient, is -1. And when x is bigger than 0, then this derivative, and therefore the subgradient, is +1. It's very easy to see. When x is 0, then the subgradient gx can be any element in the -1, 1 closed interval. To see this, we just have to use the definition of the subgradient. That is, we have to find those gx numbers with which this inequality holds. So x is 0, and therefore f of x is also 0. Since f is the absolute value function, thus f of y is the absolute value of y. Putting all this together, we have to find those values where the absolute value of y is at least as big as gx times y. From this, it follows that gx has to be in the -1, 1 closed interval. Now that we know the subgradient of the absolute value function, we can calculate the subgradient of the one norm. the one norm of x is just the sum of the absolute values of the coordinates of x. Since this is just the sum of the absolute values of the coordinates, we can see that if one of the coordinates is 0, then f of x is not differentiable in that point. By the definition of the subgradient, we just need to find those g vectors with which this inequality holds. Looking at this inequality, it's easy to see that the subgradient gx can be found coordinate-wise. That is, we just have to find those gxi coordinates where this inequality holds for all I coordinates. Now we can use results from the previous slide. When a coordinate xi is not 0, then the i's coordinate of subgradient gx is just the sign of xi, either -1 or +1. When xi is 0, then the i's coordinate of gx can be any element in the -1, 1 closed interval. To make this proof more formal, what's left is to verify that all these g vectors are indeed subgradients and there are no other valid subgradients. The next example I would like to discuss with you is the 2 norm. Let function f be the 2 norm of x. That is, f of x is the square root of x transposed x. Using the chain rule, we can try to calculate the derivative of f of x. This will be 1/2 times x transposed x to the power of -1/2 times 2x. If we simplify this, we get that the gradient of f of x is x divided by square root x transposed x. From this, we can see that f is differentiable everywhere except when x is 0. Now, let's try to calculate the subgradient when x is 0. Using the definition of subgradient, we just have to find a vector g0 such that the norm of y is at least as big as g0 transpose y for all y. So, as we discussed, we need that the norm of y should be at least as big as g0 transpose y for all y. From the Cauchy-Schwarz inequality, we know that g0 transpose y can be upper bounded with the norm of g0 times the norm of y. Therefore, our goal is to find those g0 vectors with which the norm of y is at least as big as the norm of g0 times the norm of y for all y. This implies that when x is 0, this subgradient g0 could be any vector with norm less than 1. This is the unit ball. To make the proof more formal, we just have to verify that indeed all of these vectors are subgradients and there are no other valid subgradients. When x is not 0, the subgradient of function f is simply the gradient x divided by the norm of x. In what follows, we would like to calculate the subgradient of the indicator function of a convex set C. To be able to do that, we will need the definition of normal cones. We already discussed this a few lectures ago, so now let's just quickly review the definitions. Let C be a convex set, and let X be a point in this set C. This could be either an interior point or a boundary point. The normal cone of set C at this point X is the set of those vectors G with which G transpose y minus X is less than or equal to 0. In other words, the angle between vector G and vector y minus X is at least 90 degrees. We also discussed that even if the set C is not convex, its normal cones are always convex. In what follows, we will assume that set C is convex. We already discussed that the normal cone in any interior point is the 0 vector. If X is a point on the boundary, where the boundary is smooth, then the normal cone in that point is a single ray shooting out from the set. However, If x is a point on the boundary where the boundary is not smooth, then the normal cone is a regular fat cone. Now we are ready to calculate the subdifferential of the indicator function of a convex set. Let C be an n-dimensional convex set, and let f of x denote its indicator function. This indicator function is 0 in a point x, where x is in set C. Otherwise, if x is not in C, then f of x is infinite. It's very easy to see that the indicator function is a convex function when the set C is convex. This simply follows from the definition of convexity. The main lemma that we will prove is that the subdifferential set of the indicator function at the point x is the normal cone in x. In other words, the subdifferential set of the indicator function is the same as the normal cone. We want to prove that when set C is a convex set and x is a point in set C, then the subdifferential of the indicator function of set C at x is the same set as the normal cone at x. The proof has two parts. First, we will select an element of the subdifferential set of the indicator function, and then we will prove that this element is a member of the normal cone. In the second part, we will do the opposite. We will select a vector in the normal cone, and then we will prove that it's also a member of the subdifferential set of the indicator function. So first, let x be in set C, and let gx be an element of the subdifferential of the indicator function. Since gx is a subgradient of the indicator function, it has to satisfy this inequality for all y. There are two possibilities. If y is not in set C, then the left-hand side of this inequality is infinite, so the inequality holds. If y is in set C, then the indicator function value there is 0. By your assumptions, x is in set C, and therefore the indicator function value there is also 0. Thus, gx has to satisfy this inequality, that is, gx transposed y minus x has to be 0 or negative for all y in set C. This is just the definition of the normal cone, so gx has to be in the normal cone. That is what we wanted to prove in part 1. Now, let's prove the second part. Again, first we fix a point x in set C, then we select the vector gx in the normal cone. We will prove that this gx is also a member of the subdifferential set of the indicator function. By the definition of the normal cone, gx transposed y minus x has to be negative or 0 for all y in set C. Therefore, this inequality holds. Since y and x are in set C, the indicator function values in these points is 0. So this inequality also holds, which means that gx is a subgradient of the indicator function, and this is what we wanted to prove. Let's have one more example, and let's try to calculate the subgradient of the max function. Let f1 and f2 be two functions, and assume that they are convex and differentiable. Let f of x be the maximum of f1x and f2x. It's clear that if f1x is strictly bigger than f2x, then the max function in x is f1x, and the max function is differentiable at x, and we have a unique subgradient, which is the gradient of f1x. Similarly, if f2x is strictly bigger than f1x, then the gradient of the max function in x is the gradient of f2x. The interesting case is when f1x equals f2x. One can prove that in this case, the subgradient is the line segment, or with other words, the set of convex combinations of the gradient of f1x and the gradient of f2x. The subgradient calculus is somewhat similar to the calculus of the normal gradient. If a is a positive number, then the subdifferential of a times f is the same as a times the subdifferential of f. The subdifferential set of f1 plus f2 is the same as the subdifferential set of f1 plus the subdifferential set of f2. We also have a chain rule type equation for the affine composition. The subdifferential of f of a times x plus b, where A is a matrix and x and b are vectors, is simply A transposed the subdifferential set of f at ax plus b. We have already calculated the subdifferential of the maximum of two convex functions. This can be generalized to calculate the subdifferential of the maximum of finite many convex functions f1, f2, and so on, fm. Let f of x denote this maximum function. At the location x, let's collect all the active functions, that is, those functions that achieve this maximum value f of x. Let's calculate the subdifferential of all of these active functions. Then the subdifferential of the maximum function f can be found as the convex whole of the union of the subdifferential sets of the active functions. This theorem can be even further generalized to the maximum of uncountably many convex functions. I'm showing that general theorem here. According to this theorem, the subdifferential of the max function f contains the closure of the convex whole of the active functions. Under some regularity conditions, these sets are equal and the subdifferential of the max function is exactly the closure of the convex whole of the active functions. Finally, we are ready to calculate the subdifferential of the LP norm. Using only the definitions of the subgradient, the calculations are a bit complicated, so we will do a trick. Let p bigger than 1 be fixed, and let q be a real number such that 1 over p plus 1 over q equals 1. We can prove that in this case, the p norm of x can be calculated as a result of the following constraint optimization problem. Let's calculate the maximum of z transposed x subject to the constraint that the q norm of z is less than or equal to 1. Now we can prove that the subdifferential set of the LP norm function f equals to this set. This set contains all those y vectors whose q norm is less than 1 and y transposed x equals to the maximum of z transposed x, where the q norm of z is less than or equal to 1. Let's prove this with those lemmas that we just discussed. Now, the trick is that if we define function fyx to be y transposed x, then for any fixed y, this is a function of x, and the p norm is just the maximum of these functions with constraints the q norm of y is less than 1. From the previous slide, we know how to calculate the subdifferential of the max function as a closure of the convex hole of the active functions, and we can just use that rule here. In the next lecture, we will use this subgradient to create a subgradient-based optimization method. Other than this application, subgradients sometimes can also be directly used to characterize optimality. In the next lecture, we will continue from here. Thanks for your attention.